Hello, so today we are going to take a look at this Knapsack problem, which is a famous dynamic programming problem. And the specific variant that we are looking at is bounded 0-1 Knapsack. So the problem says we get n items that are numbered from 1 to n. And for each one, we want to, basically for each item, it has a weight, wi, and it has a value, vi, right? And what we want is to choose some of the n items and carry them in a knapsack or a backpack or something. And the capacity of that knapsack or backpack is just w. We can't fit more than w weight. And so that means that the sum of all the weights of all the items that we can take can be at most w. It can be less because that can fit, but it can be more than that because we don't have space for it. And the problem asks us to find the maximum possible sum of the values of items that we can take. These are some constraints that I'm defining here. Depends. Sometimes we may get, depending on the constraint, we can solve the problem differently. But here, these are the constraints. N is at most 100. W is at most 10 to the power of 5, and the weight can be at most w. And the values can be at most 10 to the power of 9. So one thing you can see here is that the weight is smaller than the value. That will become important a little bit later, but for now let's just focus on this. And so what we want here is to solve this problem. And as you can the knapsack problem is a famous dynamic programming problem, so we know right away that we need to solve it with dynamic programming. So okay, so let's see how we can solve this problem. So since it's a dynamic programming problem, we know right away that we need to specify a couple of things. We need to know what is the goal, what are we looking after, or what result are we trying to return at the end. And then we need to define our state. What parameters should our state have? And we need to also find the base cases. We also need to define the recurrence relation between subproblems, and we need to define the order of iterations that we need, so that when we are computing a problem, the subproblem that it depends on has already been computed. And so what is the goal function here? So what we want, as the problem says, is to find the maximum possible sum of values of items that we can take. And these items should not exceed w. So right away we know that what we need to find is maximum possible sum of values of items we can take with the total weight w, right? That's the constraint that we have. So we can take w weight and all the maximum values that we can take that fit in that. That's what we are looking for. And so if we write this in terms of a state here, let's call it dp of, we need two things, I and j. We need two parameters. So we need, of course, we need to know what items have, like, what is the items we are looking at, like, and then what is the weight we used, right? So at each position we need to know the current position of the item we are looking at, and the current weight the weight that we used, right? The weight that we've taken, right? And so we can define our state with that as dp of ij, such that that represents the max value. So it should be a mapping kind of from the goal. So it should be the max value or the max possible sum we can get from the first I items. Of course, with total weight. So you can see it's a direct mapping of the goal with total weight g, right? So that's our dp of g. That means that the final result that we will need to return, we will need to get the max value from all the n items, right? So that would be dp of n. And the total weight that we need to use is w. So this would be our final result that we need to return. Now, what are our base cases, right? So what we know is that when one base case definitely is when the knapsack has no value, right? So basically, what we know is that value is 0 if we take no items included in the knapsack, right? So that means that the value is 0, right? If we include nothing, value is 0. So that means basically that dp of, no matter what the weight, the capacity of the knapsack is, if we are getting just the first 0 items, then the value is 0, right? Because we are taking nothing. Now the other condition is if the capacity is 0, the capacity or weight is 0, or total weight. That means basically that no matter what number of items we are looking at, we have 0 capacity, so we can't take anything. So that would be dp of I and 0. So these are the base cases that we are looking at, right? Now, what is the recurrence relation that we can find, right? So we know that we have 2 choices every time, right? 2 choices. Either we pick an item or not. Right? So not picking an item, while there is no constraint, we can just leave it, right? But picking an item, we can only pick an item if its weight, which is, if its weight is, well, it has to be smaller than the capacity, right? Or the total available weight. Because otherwise, well, there is no space left for it, right? So what this condition here means is just if, so the item's weight, like we call that J, right, is smaller than the available weight, let's call that maybe W, right? Only in this case that we can pick an item. Only if it's bigger, right? Only if it's bigger or equal. So we can take the item only if, I messed up something here. So let me just define J. So what is J? So J is the total weight that we have, right? By the definition of this. And so total weight here, this is J, right? Now the item's weight, let's call that, just while processing, let's call that W, right? So this means is that if J is smaller, if the total weight is smaller than W, that means that we can't take the item. So we have to leave it. Otherwise, well, that means that we can take it. Else, we can take it, but we have to try both choices because we don't know in advance which one is better, right? So here we can take the item, which means try both possibilities or choices. That's what dynamic programming does, tries everything and just picks the best one. And so here, where we can't take the item, that means that dp of ij would be, we can't take item I, right? So the value would be just the same value as considering only the I-1 items and with the same weight because we haven't taken anything. Now otherwise we have to try both. So the first one is not taking it, which is just dp of I-1 and j, and the other one is taking the item, which means, well, we have a value, right? We have a new value because we've taken the item I, so the value is, let's call it v of I, plus considering the sub-problem. So once we take the item I, well, we have to get the best solution for I-1 items. And the weight, total weight now is just j minus w of I. Why is that? Because we've taken item I, and so now we put that in our knapsack. So there is already now wi weight used in the knapsack, right? So that means that there is only j minus wi available for the rest of I-1 items to use. And so we take the max of all of these two. And basically this is this represents take the item choice, not take the item choice. So not take it. And this represents take item, right? And so now we have our recurrence relation. We know that if the item can't fit, then we have to just use that weight to consider taking the maximum value from the I-1 items. Otherwise, if we can't take it, try both choices and see which one is better. Okay, so now let's go to the next step. So now that we have our goal, our state, base case, recurrence, we need to know what is the order of iterations of our for loops. So order of iteration. So that we need to know what is the order of iteration for both dimensions of the DP array, which are I and j. So we know that I needs to go through all the items, right? And so we know that I needs to be from 1 to n, right, for all the items. But we also know that in order to get y1, because of -1 here, we don't want to get an index that isn't correct. But so since to be able to compute I, we need to already have computed I-1, right? So that means that our loop needs to be increasing, so that when we are at 2, we already computed 1. And so that means that our I needs to be in the range of 1 to n, which in Python we will need to do n+1. And what about the weight here? So the weight, we know that we also need j-wi, right? So when we are computing dp of I and j, we need to have already computed j-wi. So that means also the smaller value needs to already, the smaller weight needs to already have been computed when we are computing a bigger weight. So that means that j also needs to be increasing. So, and its max is w, and so w+1. So j is in 1 and w. And since the values are zeros here, we can just initialize the DP array with 0 values, 2D array with 0 values. And because of that, the base cases have already been set, so we don't need to set them again. And because of that, we don't need to start from 0, because that's the values for these are 0, right? Because of this base cases. Okay, so now that we know all of these, the goal, the state, and base case, and recurrence relation, we can start just applying this. So what this means is that, well, we need to first initialize our DP array, and then after that we will need to do this order of iteration, going for I from 1 to n+1, j from 1 to w+1, and then after that we will need to apply our recurrence relation, and then at the end we will need to return the final result. And so you can see, according to these two loops for the order of iteration, our time complexity would be O of, so this is O of n, right? And this is W, right? So our time complexity overall is O of n multiplied by W time. And because those are the only, we'll do this and then we'll apply the recurrence relation. So here we'll apply recurrence relation. Let's call this one. And then the space complexity is just, we are just using this DP 2D array, right? Which its dimensions are I and j that go from 1 to n, and from 0 to n, and from 0 to w. So same thing for the space complexity, it's O of n w space. Okay, so now let's write this solution, and then from there we'll see how we can retrieve the solution, not just the value, retrieve the exact items that we took to obtain the maximum possible value. Okay, so now let's try to solve this. So here is the method signature. We get n, which is the number of items, and w, and we get also the weight values. And so here is, I've written some assertions here for what the result should be. So let's just type the solution. Okay, so the first thing we need to do is define our 2D DP array. So that would be DP of, so 0 for, this is the columns, j values, and then the row values, which are the items indices. So that would be I+1. Sorry. And then we will need to do the two loops that we mentioned in the order of iterations that we came up with, and so that would be n plus 1, and j would be in a range of 1 and w plus 1. So these are the weights, and here we can get the weight values. So just one caveat here is that the weight values index needs to be I minus 1, because it's an array that starts from 0, the indexing starts from 0, and the I here is starting from 1 to represent taking the first item. And the first item here, it has index 0, right? So this is just some indexing thing. And now we can apply the recurrence that we said, which is if the weight available, the total capacity, is smaller than the item's weight, is smaller than the item's weight, that means we can't take the item. We can't take it, so we can't take the item. So at that point, we need to just do dp of ij is equal to, we can't take the item, so we just go look at the best solution for the I minus 1 item using this capacity j. And then now we can take the item, but we have to try both choices and see which one is best, is better. So we try the first choice, which is not taking the item, and then the other choice, which means taking the item. So we have value v, and we have I minus 1. So getting the best solution for the I minus 1 items, and the weight that we have now, or the capacity that we now have, is just j minus w. W is the weight of the items that we took, which is item I, right? And now at the end, we will return the final result, which is dp of n and w. And that's pretty much it. And so let's run this and make sure it passes. Reference it before assignment here. Yeah, so this is n plus 1. Okay, so all of the test cases pass. And so this is the solution that we said, and then the time complexity, as we said, is O of n w time, and time complexity. And the space complexity is same thing too, because the dp array here fits dimensions are w, n and w, so n multiplied by w. Now let's see how we can come up with the optimal solution, print or return the items that we took to obtain the best solution. For example, here the best solution would be to take this item and this one. So we get 16 plus 30, which is 90, which is the best value. And then the two items that we took are 3 and 5, that have 3 and 5 weight, which is 8, which is the maximum weight possible. And we can't find a better solution. And so for this here, what we need to have as the list of items in the optimal solution are this one and this one, which is index 0 and index 2. And so we should get, as a result, we should get 0 and 2 as the optimal solution items. So let's see how we can accomplish that. Okay, so now to get the optimal solution, what we need to do is we can start from the maximum value that we get. So we know that we have dp of nw as the maximum value for the optimal solution. And so what we can do is just basically start from here and just check, well, if the value at this one is equal to the value at the previous row, which means dp of n minus 1 w, then that means we didn't take the item, right? Because of this recurrence relation, right? That means we didn't take the item, or maybe this one was the maximum. Now, if it's not equal, that means we did take the item, and so that means we need to add it to our optimal solution. So what we can do is just have these two variables. Let's call them lowercase n, or maybe let's call them instead I and j, right? So if we start out with I being n and j being w, so the first value dp of ij would be the maximum possible value solution. We can just start at, that means we'll start at dp of nw, right, with these I and j. And then while the remaining capacity that we have, right, while the remaining capacity is bigger than 0, right, that means we haven't yet added all the items. So we'll define some array here for the items. Then what this means is that we can check if dp of ij is equal to dp of I minus 1 j. What this means is that we didn't take the item, right, because the weight is still the same. We didn't take the item. So this point here we don't add it, so don't add it. But if they are different, that means we did add the item, right? So the item I is included in the optimal solution. Included in the optimal solution. And so at this point, which means that we need to add it. So basically we need to add I, right? Now and then once we do this, well, we need to move one column, so that because we already counted the item, so we need to move one column to j minus the weight of I, right? Because we took I, so to know the rest of the optimal solution, we need to subtract the weight. And we need to move one row to I minus 1, right? We need to do this in both cases here also. We need to move one row to I minus 1. And then at the end, once the remaining capacity, which is just, we can call it j here, is equal to 0, that means we have the optimal solution, and then we can just print items. But we will need to reverse them if we want them in the right order. So maybe just items, reverse it. So we can print items and reverse them. So why reverse them? Because here we add the last item picked first, and so it would be first. So to get a last, we will need to reverse. But essentially the idea is this: start from the maximum possible value that we have, and check if the current if the value is equal to the same one for I minus 1 items. That means we didn't take item I, and so we just move to the previous row, which is I minus 1. Or it's not equal, which means we did take the item, and so we add it to the optimal solution, and then we move again one column, because the j minus, we move basically because the rest of the items have weight j minus w because we took item I, and that's pretty much it. And so let's type this pseudocode here in Python and run it. Okay, so now let's apply the pseudocode that we just came up with, and the pseudocode here is, I just typed it here, which is the same thing we mentioned, and so I'm just going to apply it here. So first, let me just put this above. Okay, so what we need is, first we will need to initialize our I and j values, right? So they start out as n and w, and we need to have a list so that we can put in it the optimal solution. And now, while we are still at, we haven't like explored all items. We keep going. We can also do capacity bigger than 0, but I will do that in different way, where j, if the capacity becomes 0, I just break. That means there is no need to try the rest of the items, because we already reached the capacity that we wanted, which means we already included the optimal solution. And now we can check if dp of ij is equal to dp of I minus 1j, which means we didn't take the item. Item was not included in the optimal solution. Otherwise, the item was included in the optimal solution. Okay, so if the item was not included in the optimal solution, all we need to do is do I minus 1, right, to go to the previous row. If the item was included, what we need to do is and then if the item was included in the optimal solution, that means that we will need to add it to the list of the items, except here, since the list is indexed from 0 to from index 0, and our I values are from 1 to n, we will need to do I minus 1 just so that we can get the right value because of the indexing starting from 0. And then we'll need to, as we said, move one row up to I minus 1, right? Because now we will need to consider the rest of the items. And one column by the weight, because we already took the item I, so our j value we will need to subtract let's do that first before changing I. So we need to subtract the weight value for the item I. And again, weight values indices start from 0. So again, we need to do I minus 1. And to get the first value, which is the weight, we just do 0 here to get the weight. And that's pretty much it. Now let's just print the list of items here. So optimal solution is items, but as we said, we added first the last item. So to get the first item first, we need to reverse it, and in Python to reverse it, we just do that. And that's pretty much it. So now let's run this. And you could see the optimal solution for this one is 0 and 2. For the second solution, the second one, it's taking this one, basically taking all the items 0, 1, 2, 3, 4. So taking all of them. And to solve this one with weight, we get total value 16. We need to take 1, this one, and then 3 and 4. If we try to calculate the weight for these, it's 5 plus 6, which is 11, plus 6, which is 17, which is the value that we get. Yeah, so that's pretty much it for finding the solution and then finding the optimal solution here.